Hi and welcome back. So let's work some examples of aromatic substitution reactions when we have a substituent already on the ring. So considering the compound that we have below, we have a substituent, and we want to know whether this substituent is ortho, para, or meta directing. So this is a weak activator because this nitrogen has a lone pair that can exhibit resonance in the ring. And we could draw resonance structures for this molecule, all the way around the ring. We have a lone pair here on that carbon in this resonance structure. Okay, and that's going to put a positive charge on this nitrogen. So this molecule also this lone pair can exhibit resonance with this oxygen outside the ring. And that's going to make it not as strong of an activator as it would be if that resonance didn't exist. So this would be a moderate activator. A moderate activator, or all activators in fact, are going to be ortho-para directors. So if we had another substituent incoming that we're adding onto the ring, it's going to go into the ortho or para position. So let's consider what our product would be for this reaction. Here we have an activator. This is a weak activator. And we have a strong deactivator. Well, it turns out that all activators trump deactivators, and therefore that's going to make this be the major determining factor. So this methyl group is going to be an ortho-para director. Well, our para position, if we're looking at the product, the para position is blocked by the NO2 group. Okay, it's blocked. The only thing that we have open are the ortho positions, and those are also meta, so that's ortho to the methyl and meta to the nitro. So this is not a very hard decision to make. Where does our bromine go? So we need to ask ourselves, what are we adding and where are we adding it? Okay, let's just go ahead and erase this to avoid confusion here. What are we adding and where are we adding it? We're adding a bromine, and we're going to add it ortho to the methyl group. So we could have put it over here, or we could put it on the left, or we could put it on the right. So we're going to add a bromine there. Now, for the purposes of this text, the author has told you to assume that you're only adding one incoming group at a time. So this would be our major product. The bromine goes ortho to the methyl and meta to the nitro. So let's consider this reaction. Here we have a hydroxy group and a methyl group. Both of these are activators. Okay, this is an activator that makes it an ortho-para director. This is an activator, also an ortho-para director. Now, this is going to be a strong activator, the OH group, because it has the ability to donate electron density through resonance into the ring. The methyl group is a weak activator. It donates through induction. So the fact is the stronger activator is going to trump the weaker activator, and the product, the incoming substituent is going to go in ortho to that hydroxy group because the para position is blocked. So we have OH on the ring, we have methyl on the ring. So what are we adding? This nitric and sulfuric acid adds an NO2 group. And where are we adding it? We're adding it ortho to the OH group. Okay, so that's going to be our major product. Now we could have put it over here on the left side. It wouldn't matter either way. So sterics can also affect where our groups go. Here we have a compound that has an isopropyl group and a methyl group. And the isopropyl group is larger, so the methyl group is going to be the major factor in determining where our incoming substituent goes. So what are we adding and where are we adding it? We're adding an NO2 group, and we're going to add that NO2 group ortho to the methyl group because it's smaller. The methyl group is smaller than the isopropyl group, leaving more room for the substituent to go there. So this is going to be the major product, and this is going to be our minor product. Okay. All right. And so if we have the opportunity to add a nitro group ortho to both of these alkyl substituents, it's not going to be observed because there's just too much steric hindrance here from the methyl and the isopropyl. The major product in this case is going to go either ortho or para to the isopropyl group, and in fact this is probably going to be your major product on the left and minor on the right. So para to the isopropyl is going to be major just due to steric hindrance. So let's consider how we would synthesize this product. We've got kind of a problem here because we want to make this bromine add ortho to this T-butyl group. That's not going to be our major or even a minor product unless we do something specific, because the T-butyl group takes up so much space, it's going to block these ortho positions. Okay, the para position, the para is going to be the major product. So if you just did this reaction with Br2 and FeBr3, then you're just going to get the bromine adding para to the T-butyl group. That's going to be your major product. But if you want to get the bromine added ortho to the T-butyl group, then we've got to do something to force that group to go ortho. And so what we do is we use a blocking group. So if we start with our T-butyl benzene here on the left, down here at the bottom, we can add a blocking group. Then we can do the bromination, which is going to force that bromine to go ortho to the T-butyl group. And then we can remove the blocking group and we have the desired product. Now what can we use for a blocking group? Well, you'll remember I told you earlier that sulfonation is reversible. So if we use that concentrated sulfuric acid, we can add the SO3H group, and then we can use dilute sulfuric acid to pull it back off. And that will give us the desired product. So here you can see that we can use concentrated sulfuric acid to give us the sulfonyl group added, and dilute sulfuric acid to pull it back off. So the overall synthesis would go like this. We use fuming sulfuric acid to form this blocking group, para to the T-butyl group, so we're going to block that para position. Then we do the bromination and install our bromine at the ortho position to the T-butyl group. Notice this is also meta to the SO3H, and that's perfect because this is an electron withdrawing group. Okay, then we use dilute sulfuric acid to remove the blocking group in order to give us the desired product. So we've seen a lot of synthesis strategies in this chapter. We've seen how to install a bromine, a chlorine, a nitro, a sulfonyl, a methyl, and an acyl group. We've seen how to convert the nitro group to an amine group, and the acyl group to reduce that to an alkyl group. You'll remember from the last chapter, if we have a methyl group, that's going to give us a benzylic position. We can brominate to give us the tribromo on that carbon, and we can oxidize to get a carboxylic acid at that position. So we've learned how to make all of these different reactions, do all of these different reactions through electrophilic aromatic substitution. Okay, and so we can go ahead and work some additional problems with that. And let's go ahead and think about that. So I'm going to work, this is from version 2, problem set, let me see. I'm going to go ahead and work some from problem set 19.22, but I'm going to alter it a little bit so we can determine what an incoming group would be. So the question is, for each of the following compounds, determine the position that is most likely to be the site of an electrophilic aromatic substitution. Okay, that's fine, but let's go ahead and do a reaction at that site. Let's go ahead and see what our product would be. So for the first one, we have a phenol derivative. Okay, so what would be the most likely site of electrophilic aromatic substitution? OH is an activator, NO2 is a deactivator, and methyl is an activator. So our activators are ortho-para directors, and our deactivator is a meta-director. Okay, so where are our positions? So for our OH group here, this is ortho. These are ortho positions to the OH, and this position is para to the OH. Okay, so let's go ahead and change colors. Let's look at our nitro group. This position is meta to the nitro, so remember a deactivator is force meta. And this position is also meta to the nitro. Okay, and then we have here this weak activator, this methyl group, and incoming groups are going to be ortho to the methyl, which is here and here, or para to the methyl. So most of these are blocked, but the thing is that the OH group is our strongest activator, and remember, activators trump deactivators. Okay, so what is going to be the most likely position to be to receive an substitution in an electrophilic aromatic substitution? The most likely position is going to be ortho to that OH group because it's a strong activator, and activators are ortho-para directors, and our para position is blocked. Okay, so these two ortho positions are going to be the more likely positions. Now here with this nitro group, this is large, and it's going to somewhat block this ortho position from being substituted. So our more likely position to get a substitution is going to be this other ortho position. So this is going to be the carbon that's going to undergo substitution on this particular molecule. So let's go ahead and consider what our product would look like. So we're going back and redrawing our starting material here. Okay, and let's say we're going to do a bromination. Sorry, Br2, FeBr3. Okay, so that's going to install a bromine on the ring, and it's going to install it at that position that we just looked at. So bromine goes here. Okay. All right, let's see if we can look at maybe one more of those, if we've got enough room. Let's consider C from that. series. Okay, so where would be the most likely spot for electrophilic aromatic substitution? Let's say we're doing a nitration. Now it doesn't matter what the incoming group is. What matters is the groups that are already on the ring. So our incoming group here is going to be an NO2 group. If we use nitric acid and sulfuric acid, this position is ortho to these T-butyl groups. Okay, this one is para to the first T-butyl and ortho to the second. This position is also para to the first and ortho to the second. Okay, so this position at the top, let's call them A, B, and C. Position A is going to be completely blocked. It's going to be very difficult for anything to add there. So positions B and C are going to be equally likely to be substituted. Okay. So in this case, we're adding an NO2 group. We'll just pick one. We'll put our NO2 right here. Go ahead and work B while we're at it. Okay. Here's our starting material. Okay, so we have an electron withdrawing group that is a deactivator, so that's going to be a meta director. We have an electron donating group that's going to be an ortho para director, and this is a strong activator. Okay, then we have a bromine that is a weak deactivator, but also an ortho para director. So the one that's going to determine where everything goes is this one right here. Okay, this methoxy group is a strong activator and an ortho para director. So here is an ortho position, here's a second ortho position, and the para position is blocked by the bromine. Let's call these positions A, B, and C. Position A is blocked by that nitro group, and therefore the incoming group is going to be installed at position B. So let's consider, let's say we're going to add a chlorine. So what are we adding? We're adding a chlorine. Okay, now we're going to install that chlorine at position B. Okay, so that's how we work those problems when we have multiple substituents on a ring. So we've seen all of these reactions. If we have a nitro group, we can get an amine simply by reduction with zinc and HCl. If we have an acyl group, we can get an alkyl group with zinc and HCl. If we have a methyl group, we can get a acid with an oxidizing agent. If we have a methyl group, we can get a tribromo with, say, something like NBS. Okay, because this is the benzylic position. Now, once we do that, notice that we're changing the directing potential of each of those groups. When we change a nitro to an amine, we've changed it from a meta director to an ortho para director. If we change an acyl group to a alkyl group, we've changed it from a meta director to an ortho para director. If we change an alkyl group to an acid group, the acid group is electron withdrawing. So we've gone from an electron donating group to an electron withdrawing group. We're going to go from an ortho para director to a meta director. If we go from an alkyl group to this CBr3 group, we've gone from an ortho para director to a meta director because the methyl group is electron donating. So that makes it an activator and an ortho para director. The CBr3 is an electron withdrawing group. That's going to make it a deactivator and a meta director. Okay, so we've changed the directing activity or the directing potential of the group that we had on the ring. So we have to consider what we have on the ring and when we need to make that conversion for our synthesis problems. We also need to consider whether we need a blocking group on the ring. So if we were going to do this particular reaction, I'm sorry, this is something else. If we're going to do a nitration, we can't do that. We can't add a nitro group in the presence of an amine group, okay, because it's going to lead to an oxidation of the amine group and give us unwanted side products. And so you can't, that's one caveat to this reaction. You can't do a nitration in the presence of an amine already on the ring. I don't think that's something I'd really expect my students to know. But if you're not in my class, it may be something that your professor expects you to understand. Okay, so here's another caveat. Friedel-Crafts alkylations and acylations are too slow to occur if you have a deactivating group already on the ring. So you're not going to get a reaction there. Okay. And again, I probably wouldn't dock my students for doing that on an exam, but your professor may be a little bit more strict. So if we want to design a synthesis for this molecule, this is a pretty tricky one. We got kind of a problem here because we've got these two acid groups. Now remember, an acid group is a meta-director. And we're going to start with benzene. So we can't have an acid group on there when we add that second acid group, or it's going to go meta. It's not going to go ortho. And another thing, generally when you put the first group on, if you've got an ortho-para director, the incoming group is going to go para instead of ortho if it takes up a lot of space. So to get a good yield for this product, we're probably going to need to start with, we're going to need to use a blocking group, okay? So if we looked at this retrosynthetically, then what would we have gone back to? What would have been our thing that we had just before we got to that diacid? It probably would have been two methyl groups here, because we could have converted those methyl groups in one fell swoop with an oxidizing agent, right, to the acid groups. So we could have used potassium permanganate or Jones reagent at these benzylic carbons in order to get the acid, okay? So how would we make this? How would we make this species right here with the two methyls? Okay, so this is orthoxylene. How would we make orthoxylene? Okay, well, we would have had to use a Friedel-Crafts alkylation to get those methyl groups on the ring. So if we go back a step, we would have had to have one of the methyl groups on the ring, right? Okay, and then we had to go from here to here. We would have had to put that second methyl on. But we've kind of got a problem there, because once we go back to benzene, we can put that first methyl on, no problem. We can use CH3Cl and AlCl3. We can do a Friedel-Crafts alkylation. But we can't just do that again and go from here to here. You might be able to get a significant yield of the ortho product, but very likely not. Your major product is going to be the para. So let's consider, let's do a little side reaction here. So the next thing we're going to have to do, if we call this A, B, so we're going to use chloromethane and aluminum trichloride to first, starting with benzene, to convert benzene to toluene, okay? And then we're going to have to do a little side reaction here. We're going to have to install a blocking group on molecule B to block the para position so that the second methyl group doesn't add there. So how do we do that? We just use concentrated or fuming H2SO4. Okay, so now that we have a blocking group, we can go ahead and add the second methyl group, so we're going to use chloromethane again. And then we can unblock with dilute sulfuric acid. To give us the orthoxylene that we wanted. Now once we get to that's our molecule, let's call that C here. Once we get there, all we have to do is oxidize with something like potassium permanganate to get the acid. And that will give us our target molecule that we wanted. So let's see if we can design a synthesis for this particular product. Okay, so we've got a bromine, we've got a nitro, we've got an acyl group on the ring. Now if we just wanted to go back to the last group that we need to attach, would we be attaching the nitro group last? Okay, why can't the bromine or acyl groups be attached last? That's an interesting question. So we have to think about what the direction should be for each particular group. So if we're starting with benzene, we can add the bromine first. Then if we add that acyl group next, it's going to go para in general to the bromine. Okay, remember that acyl group is going to be a deactivator and a meta-director, and the bromine is an ortho-para director. So it's better if we add those two first, and then that's going to put our nitro group right there where we wanted it, because it's meta to the acyl group and ortho to the bromine. Okay, both of these are deactivators though, and therefore our yield may not be very high. Okay, so that brings us to the end of this section of the chapter on electrophilic aromatic substitution. I'll get back to nucleophilic aromatic substitution and elimination addition next time.